Welcome to GCSE Astronomy. In this video, we're going to look at Earth as a globe. The first word we need to define is the word axis. Now, the axis of something is normally a point around which something could rotate. So the axis of the Earth is the imaginary line that goes into the North Pole and out of the South Pole. It goes right through the centre of the Earth, and the entire Earth turns around in its daily motion around this point. It means that a place on the equator is actually moving in a very large circle, and whereas here in the UK we'd be going around in a smaller circle, but if I stood on the North Pole, I wouldn't be going around in a circle at all. I'd just be rotating on the spot. Now, as the Earth curves around from the North Pole to the South Pole, the sun's light is coming in approximately horizontally. And because of that curvature of the Earth, what we find is near the equator, the sun's light is falling almost directly down. And so it's spread out over quite a small area. And so that actually gets quite a lot of energy. But at the pole, as the curvature of the Earth goes over, the sunlight is actually now being spread out on a much larger area. And so therefore it's being shared out more. And so the actual energy per land area is much less. That's why it's much colder at the pole. So what are the poles like? Well, here are two photographs of the South and the North Pole, but they're very different from each other in terms of what they're physically like. For example, if I went to Antarctica and I visited the South Pole, not only would I find the South Pole present on a 2.7 kilometer thick ice sheet resting on bedrock down below, I'd also find that there is permanent cabins and an Antarctica base, a polar base doing science on the South Pole all the time. Temperatures are extremely cold down there, ranging from minus 82 to minus 12 degrees Celsius. So at all times, you have to wear protective clothing. At the North Pole, however, it's very different. The North Pole is actually under the sea. The Arctic Ocean sits over the North Pole. It's about 4.5 kilometers down to the seabed, but a thin veneer of ice forms on the surface of the water. So you can stand next to the North Pole, but it's on basically an ice flow. This ice flow is constantly moving. So if I put a marker to mark the North Pole one year, I'd find that marker several kilometers away the next year. It's not permanent. Because it's on an ice flow, you can actually reach it by ship or submarine. And with global warming, the ice is getting less and less stable. And so there will be a point in the future where the North Pole is open ocean. Now, interestingly, these two places, even though they're quite different in their how they physically are, they experience the same kind of astronomy. They both have polar nights, and they both have midnight suns. Let's explore a little bit more about what you would expect to see if you were near the poles. So the polar region is defined by this thing called the Arctic Circle. It's an area of land on the Earth which lies within 23.4 degrees of the North Pole. But why 23.4 degrees? Well, it turns out Earth's axis is not straight up and straight down relative to the rotation of the planets around the solar system. It's at a slight angle. And we'll look a little bit more at why it's at an angle a little bit later. But being at an angle means that sometimes the North Pole is pointing towards the sun a little bit more than it normally would, and sometimes it's pointing away from the sun, like the South Pole is in this top diagram. It means that everything within 23.4 degrees experiences some pretty incredible astronomical phenomena. So here is the Arctic Circle, and here's a photograph of me stood at the Arctic Circle there in Norway, and that's the Arctic Circle base. The Arctic Circle runs through Russia, Finland, Sweden, Norway, the very top tip of Iceland, Greenland, Canada, and Alaska. And now on this position, it's actually 66.55 degrees north in latitude, and that is basically 90 minus the axial tilt, 90 minus 23.5. More about that later. Now, let's talk a little bit about polar day and polar night. When you're within the Arctic Circle, you're further north than the Arctic Circle. There are times of the year when either the sun does not set and that it stays up in the sky all day and all night long, and there are times of the year when the sun does not rise, when it stays below the horizon all day and all night long. And this is the polar day and the polar night. The polar night lasts 24 hours, it doesn't come up, and the polar day lasts all day long, and you can see the midnight sun. What is this thing called the midnight sun? Well, if you travel into the Arctic Circle, but you are on the nighttime side of the Earth, you can be so high that what is actually happening is, and the Earth is so tilted over, you can peek over the top of the nighttime Earth onto the daylight side. And in fact, you can glimpse the sun when it is on the other side of the planet, looking over the top of the North Pole. This is a photograph of me at Nordkapp in Norway, and you can see in the distance there is the sun. Now, for me stood there, it is the middle of the night. It is 12 o'clock at night, and the sun is still visible over the North Pole in the middle of the night time. Now, of course, we use night normally to represent it being dark. I just mean at 12 o'clock at night. And so it's an incredible astronomical phenomena, the midnight sun. There is at the other side of the world a thing known as the Antarctic Circle. It is, whereas the Arctic Circle was 66.6 degrees north, the Antarctic Circle is at 66.6 degrees south, which is 90 minus 23.5, the axial tilt. It's the same size as the Arctic Circle, it's just on the other side of the planet. Now, the Antarctic Circle is actually a lot harder to get to. It doesn't go through so many countries. It only crosses land in a few places of Antarctica. The only things that get to observe the midnight sun in these places tend to be penguins. Now, we use this word, the equator. The equator is as far away from the North Pole as it is from the South Pole. It is a horizontal line that goes around the globe. This separates the northern hemisphere from the southern hemisphere of the Earth. Now, it is possible when you stand on the equator that if it is an equinox, this is the midpoint between the summer and winter, and we'll talk more about that later. So we're talking about the 22nd of March or October, then the sun shines directly overhead of the equator. The sun actually crosses over the equator. And it goes there, and you can see all of the countries there that the equator passes through. You think, why on this map does it appear to not be running through the middle of the diagram? Why does it move through why is it nearer the bottom of the diagram than the top? That's just the way that we present our maps. Because there is more landmass in the northern hemisphere, we've actually pulled the map up a little bit and we ignore part of the bottom. So we don't tend to include Antarctica on the map. We tend to look at the countries at the top because that's where most people live. And so that is the equator right there. Yeah, so on these days, on the equinox, the sun shines directly downwards. Look at this image here. It shows a no-shadow day. At noon on these days, that's the middle of the day, the sun shines directly downwards. And objects, they do not have a shadow because basically they are sitting on top of their shadow. It's a very unusual phenomenon, and if you're ever at the equator on those days, you should go and observe this. The civilization of which we are a part began in the Mediterranean and spread out from there. Those countries that surround the Mediterranean had that head start of history, and from there, written accounts of exploration are first found. And that means we have a very northern hemisphere perspective on the exploration of the world. Now, the first northern hemisphere explorer that we know about in great detail was Ferdinand Magellan, and he sailed around the world for the first time. It followed just after the discoveries of Christopher Columbus. Ferdinand thought, well, what if I sailed to this newly discovered new world and headed south? Could I get all the way around the world? Now, poor old Magellan was killed along the way, and 2 of his ships were sunk, but one of the ships came back and confirmed that if you sailed far enough in one direction, you would go all the way around the Earth, proving, of course, the Earth was a globe. Now, Ferdinand Magellan didn't just do this. In heading south, he was the first person to knowingly cross the equator and go into the southern hemisphere, where he then observed the southern hemisphere sky. Now, I say he's the first person to do it. There were already people living there, indigenous people, but the first person whose accounts are written down that were brought to those northern hemisphere countries where the civilization of which he was a member was present. So anyway, he went into the southern hemisphere, and in the night sky, he observed stars that no northerner had ever seen, including these two great big blobs in the sky near the Milky Way. They are called now the Large and Small Magellaниc Clouds, not Magellantic, Magellanic Clouds, after Magellan. And these are, we've now realised, dwarf galaxies that have been attracted towards our large Milky Way. Now, these aren't the only lines that are horizontal on a globe, if you've looked. There are these two things, the Tropic of Cancer and the Tropic of Capricorn. They are 23.4 degrees above and below the equator, respectively. And so what do these represent? Well, these represent the furthest point north of the equator that the sun can ever appear directly overhead. You see, at midsummer, the whole Earth is tipped over, meaning the sun is not directly overhead the equator, but is actually directly overhead a bit of land 23.4 degrees around the Earth. That is, in this case, the Tropic of Cancer, and it's a line that goes through Mexico, North Africa, and Southeast Asia, and then across the Pacific Ocean. Alternatively, in the northern winter, the sun is directly above the Tropic of Capricorn, which is 23.4 degrees south of the equator. Now, the sun is always directly overhead of somewhere in between the Tropic of Cancer and the Tropic of Capricorn, and it has this seasonal variation, going up to the Tropic of Cancer in midsummer and going down to the Tropic of Capricorn in midwinter, crossing the equator twice, the equinox on the mid-spring and in mid-autumn. And in between these two lines, we call this area of the world the tropics, and they enjoy tropical weather, which is like delightful. So as well as these lines, which are all 23.4 degrees either away from the poles or the equator, we can actually measure from the equator up all the way to the North Pole. It's handy for us to be able to give an idea of where we are. So with the equator, we describe as 0 degrees of latitude, and the North Pole plus 90 degrees, or 90 degrees north, and the South Pole 90 degrees south. And we actually divide it like the angle of a protractor from 0 degrees up to 90 degrees, 45 degrees running through mainland Europe. Here in the United Kingdom, about 52, 53 degrees. And so we can always say how far around the world we are from the equator by measuring our latitude. Now, this is one of the two main numbers that we need to locate ourselves on planet Earth. Can we measure latitude right here, right now, anywhere? Anywhere on Earth? Yes, we can. And don't worry, you don't need to know the details of this for GCSE astronomy, but it's kind of interesting to know that we can. All we need is to stick a stick into the ground and measure the shadow at midday. Now, by measuring the shadow, we can work out the angle above the horizon of the sun. This is called the sun's altitude. Now, this is h in the formula down here. Now, 90 minus h tells us something about our position, but the issue is here, is if we did this on the equinox, the sun's declination, so this is the midpoint of spring and the midpoint of autumn, the declination of the sun would be 0, because where it is on the celestial sphere is right above the equator. But at any other time of year, it is not. The sun drifts northwards as the Earth tilts downwards. And so we need to know at any particular point in the year what the sun's declination is. And we have to add that into our calculation. And so the way we can add it is by this formula at the bottom here, 23.44 degrees multiplied by the sine of 360 divided by 365 multiplied by d, where d is the day in the year. So 1st January would be 1, and the 31st of January would be 365 minus 81. So you don't need that for GCSE astronomy, but you could put the date into that formula, work out what the declination of the sun was today, and then measure the shadow of a stick. And with that shadow of the stick, find the altitude, how high in the sky above the horizon the sun is, and work out your latitude. It's just nice to know that you can do it. So here you go. If you need any help measuring the altitude of the sun above the horizon, you just need a stick. And the stick, it can't be so long that the shadow becomes blurry. It has to be a reasonable size, about the same size as you, thin enough to be able to measure exactly how long it is compared to how high the stick is, and you can use trigonometry to work out the angle the sun must be to cast that shadow. So the angle, if you see the little guy there standing near the end of the shadow, the angle is basically between the floor and the hypotenuse that's made out by that triangle. Tan of the altitude is equal to the height of the stick divided by the length of the shadow. Now the stick in this situation, and in all situations where you have a sundial, is called a gnomon. Isn't that a great word? Now, the only problem with this is that you can't do this on a ship. You can't stick a stick in the sea and hope that it's still there. It's in fact, because of the movement of the ship, you can't even stick it into the deck. So there had to be invented some sort of handheld way of measuring the altitude of the sun above the horizon. The cross staff at the end of the sort of medieval period was a great way of doing it. You had a stick and you lined a part of it with the horizon, then you looked at the sun where it appeared. Problem was, it blinded most of the sailors that used it. Now bear in mind, this is the only way that people like Christopher Columbus used to figure out their latitude, and Ferdinand Magellan used. These were the tools of the time. But fast forward a little time into the 1590s, about the time of the Spanish Armada, a new tool came in, and it was called the backstaff. It basically enabled you to make the same measurement but use the shadow of called a shadow vane, like a little tiny gnomon, but putting a shadow onto something else. It meant that you were looking at where the shadow fell rather than directly looking at the sun. And so that enabled you to measure the same angle but without blinding yourself, which everyone agreed was much better. Into the 1730s, and people going around the world now, we needed much better ways and more accurate ways of measuring our position. So this tool, it's called the sextant. That's because it's 1/6 of a circle. It has a little tiny sighting telescope, a little mirror, some little filters to block out the sunlight, but it's basically a glorified version of the backstaff. And the bit at the bottom slides around and you can read off exactly the altitude of the sun at midday, put it into that formula and work out your latitude wherever you are on Earth. Now this tool is so accurate that they're still carried by ships to this day. Just in case they have a complete blackout of their GPS system, you can always figure out your latitude on this Earth just by having a sextant. Now, astronomers haven't always measured the altitude of things for the sake of knowing their location. Astronomers have been just interested in finding the altitude of things so that they can map their position in the sky. And all the way back to the ancient Greek astronomer Hipparchus, who was the very first person to actually take measurements that accurately positioned the stars in some kind of map. He used something called a quadrant. It's a quarter of a circle with a sighting little tube that would enable you to lock onto the star, look through the tube, and then it read off exactly its position above the horizon. Ptolemy used this as well, the person who developed the Earth-centered model of the universe. You might have heard of him. And then moving forward into the Islamic Golden Age, Muhammad ibn Musa al-Khwarizmi, he used this and catalogued much more of the fainter stars. Many of the stars in the night sky are given Arabic names basically because of his catalogue. Even in the 1500s, Tycho Brahe of Copenhagen, whose very important astronomical measurements fed into Copernicus and Kepler's first attempts to understand the sun-centered model of the solar system. He took most of his measurements with a really sensitive quadrant. And you can still see the quadrants at Greenwich Royal Observatory that were used 300-400 years ago for the delicate measurements of the positions of the stars in the sky. A handheld version of this, developed in antiquity, was the astrolabe. You kind of hung it, let it hang basically down, and then you rotated a thing, and they then told you the angle, and it told you many other things as well. There's lots of information that came off an astrolabe. And very primitively, they came earlier, but a person that was closely associated with the development, the accurate development of the astrolabe is a person called Hypatia. And she lived in what was the ancient Greek Empire, in Alexandria, which is now Egypt, but at the time was ruled by the Romans. And a little bit of a historical side quest here. Hypatia was present in Alexandria at the final burning of the Library of Alexandria that destroyed the last remnants of the library. This is often looked at as the end of the sort of classical intellectual period, that after that began the Dark Ages. The temples, the library, and Hypatia herself were killed by a Christian mob that thought it was all idolatrous and pagan. And so with her was lost, and with the library was lost, a huge amount of information. But luckily, many of the books and the learning and the thinking that had gone into the library had also had copies sent to other libraries in the Far East. And so that is where the intellectual journey would continue.